how to select N member using hyperspectral data. Now before that, you have some question regarding what is N member selection. N member selection, first you know about what is N member. N member collections used to select N member spectra from many sources for use in classification and advanced spectral analysis techniques. So you can run all the supervised classification techniques and many of the advanced spectral techniques from the N member collection dialog. You can run several classifications using the same N members or training classes as input by changing the algorithm technique. But before I will tell you about, first you should know about what is N member. N member is something like the spectra you have taken from the hyperspectral data, or you have seen the spectral profiles using spectroradiometer. So there are various sources of N member extraction. So first method I am going to tell you. Second method I have already told you that you have collected using ASD spectroradiometer, and you can use that spectral library for classification or for various spectral analysis of hyperspectral data. Now how to do N member collection. So for that, in NV software, go to classification and N member collection. Now here, when the input file dialog appears, you have to select atmospherically corrected data. Now in that, you can see that spatial subsetting, spectral subsetting and masking options are there. If you wanted to spatially subset the data, because you have seen that Hyperion data is very large, so you can do the spatial subsetting. And spectral subsetting, if you wanted to remove some of the spectral bands, so you can do spectral subsetting. And if you wanted to mask out some area, you can do masking also, and then click OK. Then the N member collection dialog will appear. Now in the N member collection dialog appear, if you recall that my last practical of spectral library creation, in that there are things for importing the spectral profiles or spectral library. So in this N member collection dialog, you can see that below the menu bar there are some options: file, mask, wavelength. File is telling you the name of that hyperspectral data. Mask is if you have masked out some area of that hyperspectral data, and wavelength range is written in that, and if the units are written in the header file, that is also denoted here by nanometers. Now number and range of the bands in the spectral subset you can see below the wavelength. And if the input file is not spectrally subsetted, the total number of the bands in the input file will appear in that below that wavelength menu. Now coming to the N member collection dialog, in that one table is also there below that file, mask and wavelength, that is your row number, spectrum name, and if you want you can import the names from ASCII file. So in that, you recall that spectral library creation. In that, if you import that spectra, then the spectrum name will come for various features, and then you can change the color. You can change the color of all the spectral features, the spectral profiles, because for various features, if you wanted to give your color according to your choice, you can change the colors. Now see how to import the data. The data sources are here for importing that N member are from ASCII file, from ASD binary file, from spectral library file, from statistics file, from ROI file, and from plot windows, and from N member collection file. Now you remember about that spectral library creation. In that, whenever you have saved that spectral library, spectral profiles collected from spectroradiometer, if you have saved it in ASCII file, then you can use that here. ASD binary file denotes that analytical spectral device binary file, the data, raw data imported from the spectroradiometer. And spectral library file, whatever data you have imported and you have created your own spectral library, that you can use it here. From ROI file, ROI, if you have created some ROI, you have taken the mean spectra of that region of interest, you can use that also. And if you have some statistics file, you can use that for end member collection. And from plot windows, if you are using atmospherically corrected data, you just right click that hyperspectral data window, and you can see the Z profile. And if you will click over in that option, there are options for collecting the spectra from various part of the image. So you can save that as spectral library, and you can also use for your further process of hyperspectral data. Now these are the various sources, as I already told you. ASCII file, the spectrum imported from ASCII column data file. ASD is your binary data file which you have taken from analytical spectral device, that spectroradiometer. The spectral library, you have saved it in the form of .sli. And ROI mean the mean spectrum from either an ROI or a vector. And stats file, that you have imported from the NV statistics file. Now plot, I told you already, from the image you directly right click the window in the window, and you can save the Z profile, that is your image spectra. Now this pixel purity index, before pixel purity index, I would like to tell you that before that you will have to do minimum noise fraction. After doing minimum noise fraction, first know about what is pixel purity index. This is used to find the most spectrally pure pixels in multispectral or your hyperspectral image. This typically corresponds to mixing end members. The PPI is computed by repeatedly projecting n-dimensional scatter plots on a random unit vector, and the NV records the extreme pixels in each projection, those pixels that fall onto the ends of the unit vector, and it notes the total number of times each pixel is marked as extreme. Now how you can identify the extreme pixels? Now suppose you have two band data. Now in two band data you have drawn the scatter plot. So if there are two classes, those two classes are lying on the edges of that line. Suppose if some classes are lying between that line, in the middle of that line, then that is known as the mixed pixel. If it is lying in the extremes of that line, then there are two features. Now suppose for three classes it is showing, then one triangle will be made. The vertices are the extreme or pure pixels, and the other pixels which is in between the which is in the edges of that triangle, that is denoting the mixed pixel. So the PPI function can create a new output band or continue its iteration and add the result to an existing output band. The PPI, I told you that it is typically run on an MNF transform result. So after excluding the noise bands, and the results of the PPI are usually used as input into NV's n-dimensional visualizer to visualize that which pixel is the purest and to export the spectra using that purest pixel. Now how to do that pixel purity index? For that you go to spectral pixel purity index and fast new output band. Now here you can select your MNF component, that is minimum noise fraction component image. Now here three things are there: spatial subsetting, spectral subsetting, and mask band. Now here also you can do the spatial subsetting and spectral subsetting. You can select after removal of those noisy bands, and you just click OK. Now why we are using fast pixel purity index? Even you can choose a disk based PPI index or a fast PPI method. So these are the synonym of disk based PPI method. The fast PPI method places the image data into memory and performs the computations in memory, which is much faster than the disk based PPI method but requires adequate memory. Use spatial and spectral subsetting or a more sparse array of the data through subsample resolution to fit the image data into memory, and NV informs you of the amount of memory necessary to perform the fast PPI and prompts you for continuation. When you will run that fast pixel purity index and new output band after selecting the MNF, then it will prompt you that how much memory is required for running this process. Then after, you just continue that, and when using PPI, you also have the option to create a new output band or to add to an existing output band. Now here, after that, fast pixel purity index parameters will open. In that, you can see some of the parameters are there: number of iterations, threshold factor, X resize factor, Y resize factor, and output result to file or memory. Now number of iterations, so as you increase the number of iterations, it will give you the most spectrally purest pixels. So you can see, enter a number of iterations value. With more iteration, NV does a better job of finding the extreme pixels. So balancing the number of iterations against the time available, as each iteration ran takes some time depending on the CPU and system load. Typically thousands of iterations are required for imaging hyperspectral data. But in this case, you can see in this plot, I have taken by default 10,000 number of iterations as 10,000, and the resulting image header file will list the number of iterations run. So whatever PPI image will be generated in that header file, that number of iterations are there. Now threshold factor, why we are entering threshold factor? It depends upon whatever data you are going to process. So enter a threshold factor value in data units for extreme pixel selection. For example, a value of 2 flags all pixels greater than 2 DNs from the extreme pixels, both high and low as extreme. So this threshold selects the pixel on the ends of the projected vector. So the threshold should be approximately 2 to 3 times the noise level in the data. So when using the minimum noise fraction data, which normalizes the noise, a digital number is equivalent to 1 sigma, that's standard deviation. So a threshold value of 2 or 3 works well. So large thresholds cause the PPI to find more extreme pixels, but they are less likely to be pure end numbers. So the limitation of threshold is there. Now subsampling the data. The X resize factor and Y resize factor fields are only available when you select the fast new output band option. To subsample the data and help fit them into the memory, enter X resize factor and Y resize factor values less than 1. For example, a resize factor of 0.5 uses every other pixel. However, you should not subsample less than 0.25 or every 4th pixel, because extreme pixels may be discarded then. Then after, you just click OK. If you are using the fast PPI, a dialog appears that indicates the amount of memory that I already told to you. So after running that, this is the PPI image. So you can see that whatever purest pixels it is able to identify by using those parameters, you can see in this image. Now after running that PPI, you just find out that common ROI, region of interest, you can select for your PPI and for your MNF image, because you have seen that maximum informations are there in initial components of minimum noise fraction images. So just select the common ROIs. Then after, you go to spectral and then n-dimensional visualizer and visualize with new data to see that in extremes what pure pixels are existing. So after selecting some common ROI for both the images MNF and PPI, now here whenever you will select that n-dimensional visualizer, it will ask for input file. So in that case, the input file will be your minimum noise fraction image. Now after selecting that, you can see two windows will open: n-dimensional visualizer and n-dimensional controls. Now in that 20 components are there, you can see in that ND controls. So I have selected 1 to 7 bands. Now for that, whatever pixels I have selected, you can see in the n-dimensional visualizer. Now if you want to see the axis of those components, you go to n-dimensional controls options and go to show axis. Then you are able to see the axis of all those components. Now after that, you can increase or decrease the speed, and you can view the pixels whatever is coming at the extremes of those axes. Now after that, pixels, you can select whatever extreme pixels you have identified. You can select that and you can export that as class. And for new class selection, you go again to n-dimensional controls and go to options, class controls. And after that class controls, you go to class and select new. Then after, you can again select some new classes from the n-dimensional visualizer. After that, how to see that Z profile, that whatever purest pixels you have identified, you go to n-dimensional controls and go to Z profile. Now it will ask you that which input file will be associated with that n-dimensional visualizer data. So after seeing that purest pixels from n-dimensional visualizer, you identify or you export all the purest classes, and then after you do this process, options, Z profile, and then after it will ask you which input file will be associated with n-dimensional data. For that, you just select your atmospherically corrected data, and then after selecting that, you go to that pixel, that ND profile will be open then, and then you just click over all the pixels, whatever purest pixels you have identified as extreme, you just click over that. In that ND profile it will be coming, and whatever classes you have selected, that is visible in that spectral plots. So after that, you can save that spectral profiles whatever you have exported using n-dimensional visualizer. You can save plot as spectral library or ASCII file. So now you remember my practical exercise of spectral library creation. So similar thing you can do. You can see the plot key, whatever spectral profiles are there, for which number of pixel is there, that XY axis. You can even change the color of that profiles. You can edit those spectral profiles, the data parameters. You can see the pixels, you have identified the locations of that pixel, so you can see what feature is there in that pixel, and after that this profiles you are going to give as input for your classification of hyperspectral data. And if you have any query, you can contact me on my email ID, that is vinaykumar@irs.gov.in. Thank you.